Right. As you can guess, I'm not Annette and Teije. Annette is sitting over there. This is work joint from us. Thanks for staying until the end of the conference, right? So the only benefit of having this slot in the conference is that you can quote other people's slides. So, but that's about the only advantage of this slot. So I'll talk about the systems that learn and reason. And as Scott said, until recently, we had a group called the Knowledge Representation and Reasoning Group, and we canceled the group and we renamed it. And now we are called the Learning and Reasoning Group, because we really think that this is the next big question in AI. Is, we know how to do KR. I think this conference is a great example of how we really know how to do KR, all the way from theory to serious technology stacks. We also increasingly know how to do reasoning, how to do learning. We don't know how to do the two together. So that's what today will be about. Let's see, this is the usual, now the slides don't move, yes. So I promised that I would quote a slide, but actually it's only a part of your slide. So I thought this was a really interesting corner somewhere hidden on your slides. This was a super short summary of what did we do in the past and what are we doing now, right? The whole talk will be about this one line in one corner of one slide of Chris's talk. So about the connection between reasoning and learning. And many of you will have a background in AI, will be familiar with AI, and then you'll know that AI, the history of AI, is a little bit like this, right? It's a tale of two towers, right? You're either in the statistical tower, and then you think data and learning and statistics, or you are in the symbolic tower, and then you think logic and knowledge and deduction. And it is the analogy is very well chosen, I think, because the people in the other tower are evil, right? And I also had another slide where I compared them as two religions, right? And like in real life religions, the people from the other religion are wrong, right? And you don't need to go to their meetings, called church services or conferences. You don't need to go to their meetings because they're wrong anyway. You don't need to read their books, right? Their holy books or their science books, because they're wrong anyway. And it was like that for a long time in AI. And fortunately, in the last maybe half decade, last 5 years or so, this is really beginning to change now. Now there's actually insight that there is a value in what both of these tribes do and how can we combine them. And it's also a very natural thought, right? That because, of course, our brain does both, right? Our brain does both learning and reasoning, right? And don't, of course, take this in any way seriously as the topography of your brain, but this is a picture illustrating the Daniel Kahneman intuition about system 1, system 2 thinking, right? Sometimes called thinking fast and thinking slow, right? Whereas thinking fast is things like our reflections and our intuitions and our visual system, and thinking slow is things like analytics and reasoning and problem solving. And just to get you a little bit of an intuition for what for these two different systems, I'm going to play one little game, audience participation. You don't have to raise your hand. You just have to think for yourself. I'm going to show you a picture with a question, and you'll think of the answer, and you have to record for yourself how long it took you to think of the answer. Okay, 3, 2, 1. Okay, right. Okay, so we all know who that is. It's our favorite past US president. And so it took you maybe what, 1/10 of a second? That kind of order of magnitude, right? So that's very fast thinking. Actually, you didn't even realize that you needed to think. This is almost instantaneous. Now let's do this again, okay? Another question, and you're going to, so this is the thinking fasting, right? Now you're going to answer the next question, and again, think of how long does it take you? 3, 2, 1. Who was his predecessor? Okay, exactly, Obama, right? So that was easy, right? So that maybe took you a little bit longer, but not all that much longer, right? So it was maybe not 1/10 of a second, maybe 2/10 for the Americans, 1/2 a second for the Europeans, but it's still fast, right? Okay, we'll do it one more time, right? So 3, 2, 1. Who was his predecessor's predecessor? Right? Was it Bush? Was it Clinton? Was it okay? So now you're on your way to like a second full of. So now you're on your way to a second worth of thinking. All right. So that is really slow thinking. Okay. So there's these two different systems in your head going on, and the different towers, the different schools of AI. Now they really kind of correspond to that thinking fast, thinking slow, the knowledge driven or the data driven. Okay. So now that I've hopefully convinced you that, yeah, we do have these two different types of systems, and they are very different in their kind of questions they answer and at what speed they do that. Let's look at the different results from these two different towers in AI and compare their strengths and weaknesses, right? So just gonna compare the data-driven and the knowledge-driven methods, okay? And this is, of course, very shallow comparison. Now, there's much deeper papers about this, but in slideware, it'll look a little bit like this. I'm gonna take you through this table, right, where the symbolic and the statistical approach are being compared on construction cost, scalability, explainability, and generalizability. Right, so we know that these knowledge bases are expensive, right, and so many of the talks of the past 2 days, they are about these really incredibly impressive knowledge bases, right? Some of the biggest and best ones that we built, and they're like years and years of effort, right? So the estimate for SNOMED is 40 years of effort. Right, thousands of updates every year. So this is never finished. This is really an expensive process, and this is people have dedicated their lives to building these things. So this is called the knowledge acquisition bottleneck, right? And of course, in the medical domain, this is also well known, right? If you ever try to build any medical decision support system, now you're facing this knowledge acquisition bottleneck. That's a well-known phenomenon, even back from the 90s. But there is also this construction cost at the other end, namely the data hunger, right? The machine learning algorithms, they work better with more data and they don't work with little data, right? So this is data sparsity or data hunger, right? I always get a little bit annoyed when machine learning people talk to say a medical expert, and then they say, well, no, I can't solve your problem because you don't have enough data. And I think, no, you don't have the right algorithm, right? Because your algorithms require so much data. So that's a real disadvantage of these things. Okay, scalability, right? Well, they both have their limitations, right? The knowledge-based systems get worse with more data, and we call it combinatorial explosion. And the statistical systems get worse with less data, and we call it sample inefficiency, right? What's the famous example? Say AlphaGo, right? Playing 45 million Go games to train. Okay, any reinforcement learning system would go through so many more loops than would be reasonable to do in practice. So those are also complementary strengths and weaknesses. Worse with more or worse with less data. Explainability. Okay, we know how to do explainability on symbolic systems, right? And that's because we choose representations there which are very close to our own cognitive representations, right? So here's some decision rule about that contains a variable, it contains a condition, and if that condition applies to that variable, then something else also applies to that variable, or some action or some conclusion, right? And so this is well known. This also dates back to the 90s. Now we know how to do explanations for knowledge-based systems, and we don't know how to do explanations for these learning systems, right? So this is the black box problem, right? This is my favorite cartoon. For those of you who can't read it, said, "Oh, this is your machine learning system." There's a man here standing on a pile of, well, okay, it's a pile of. He's standing on this pile of shit, and he says, "No." Yeah, this is my machine learning system. You pour the data into this big pile of linear algebra, and then you collect the answers on the other side. And then what do you do when it doesn't work? Well, you just stir until it works. Okay. Actually, so and a lot of, to my frustration, a lot of machine learning papers are like that. Now, we built an architecture, and then we changed it, and then we got this architecture, and then it worked. And that's the end of the paper, right? So for me, that's the beginning of the paper. right? So because there's very little theory on, and I think your paper you're really struggling to find out what architectures worked for which settings and so on. And then it's very hard to explain why they work and why they come at answers. And generalizability, they also have complementary strengths and weaknesses. We know this performance cliff from knowledge-based systems. If you ask the right question to a knowledge-based system or to a knowledge graph, you get a very good answer. If you ask a question that's not in a knowledge graph, you get no answer. Right, so there's this incredibly steep performance cliff. Right, it's either good or it's non-existent, so this is not robust against noisy and it's certainly not against incomplete data. Right, but of course also these machine learning systems have their performance cliff. Right, and that's called out of distribution generalization errors. Right, this is a well-known example where these are the stop signs as they appear in the wild. Okay, so this is not doctored in a lab. This is okay, people playing tricks with stop signs, and then the poor image recognition system all interprets them as a maximum speed limit sign. Okay, not a good idea if you're in a self-driving car. Right, and that's of course because these signs were not in the training distribution. So therefore it doesn't generalize very well. So this should give you some idea of, well, actually there is strengths and weaknesses on both sides, and often they are actually rather complementary. So, can we, it's an obvious thought, right? But if we get over this religious point of view, like, whatever the other guys say is wrong anyway, right? Now that we got over that, can we actually technically combine these two different types of systems? Right, obvious question. And this is now, I think, one of the, I think maybe even, it's one of the fastest rising subfields of AI. This is sometimes called neuro-symbolic AI, which I think is narrowing it down a little bit because learning is not necessarily only neural. There are lots of other forms of learning, but these hybrid systems that do learning and reasoning. And this is sometimes called the third wave. There have been opinion pieces about this. You can't go to a big AI conference these days, and one of the keynotes is about neurosymbolic systems, right? So Gary Marcus, Henry Couts, Arthur Gonzalez, Judea Pearl, all of the great and good of AI are now speaking about the need for this combination. So this is in science, this is called proof by authority, right? So lots of famous people say, therefore it must be true, right? Okay, well, let's try, right? So why haven't we done this yet, right? So we have the two towers. We now see that we want to combine the two. Well, okay, what's stopping us, right? Well, here's what's stopping us, a couple of things. So for a start, the representations that they use are very different, right? So this is the kind of representations that we've seen on our slides for the last 2 days, right? Ontology hierarchies or type hierarchies or all kinds of discrete. Now this is the typical modern machine learning representation, right? That's a very different world. It's a very different representation. And your paper was a really nice example of trying to inject one into the other, right? Trying to take a discrete hierarchy like that and trying to inject that into a neural network. But that's far from trivial. So that's one reason. So the representations are very different. Also, the computations we do with these representations, the reasoning is very different. Right, so the reasoning in knowledge graphs is like this. Okay, so you take a big logic base, and you take some facts or a query, you do some inference, and you get an answer. Right, this is the standard architecture that hasn't really changed since the early days of stuff. This is basically what you do with logic, right? But the inference in neural systems is very different. Okay, essentially, we're doing gradient descent. Right, so we have a very high dimensional space, and we're trying to find minima in this very high dimensional space. by following the gradient, right? So that's a very different notion of reasoning. It's not so obvious how to combine the two, right? There's a very nice paper by Adnan Darwish from a few years ago in the communications of the ACM, where he called them numerical function-based, right? Because the idea is that you're trying to minimize a function. Now, if you have a 512 dimensional space, you're trying to minimize a function of 512 variables, or model-based, right? So the word model is one of the most overused words in computer science, of course, because machine learners call that a model. But Darwish, okay, he calls that a model and says this is a function. Okay, fair enough. So there's a final reason why this integration is so hard. So the math is just very different, right? So this is the math that we were always doing in the knowledge representation reasoning group, right? Proof trees and logic and so on, right? Discrete mathematics, graph theory, logic, algebra, okay? And then suddenly we had to start reading papers like this, and sometimes I didn't even know, which page is up, right? So actually, right? So the math is so different. Now this is differential equations over continuous spaces, rather than algebras over discrete structures, right? So even inside pure mathematics, that is a very hard problem to solve. Okay. 5 years ago, we start on this journey of, can we help to solve this question of combining learning and reasoning, right? And then we get confronted with this huge pile of literature. And this pile of literature is growing at an increasing rate because so many more people now share this insight that, yeah, we really need to combine the two. So every day I get 2 emails from Google Scholar, right? One makes me happy, the other one makes me depressed. So the one that makes me happy saying, oh, your papers, the following papers by you have been cited by these people. So great. Now, a little ego booster at the beginning of the day. Great. And the next email says, and here are 20 papers you should be reading today because they're all relevant to what you do, right? That's the one that makes me depressed. And there's this, it's really hard to keep up with this. And that's even harder because there is very little structure to this literature. This literature is growing fast and it's very young. There is a long history, but the history is very thin. And now it has suddenly exploded. There is no clear structure to this literature. There's no clearly identified families of systems, ways to find your way around this literature. So we thought, well, can we come up with a language or a schema or some categorization idea to categorize this literature, to create some order in this chaos of hundreds and hundreds of papers. So we tried to read the literature. Okay, that's not fast enough. Then we organized a seminar course, which means that you make your students read the literature. So that multiplies your reading power by a factor of 20. But it's still not enough. So we thought, okay, we really have to create some intellectual structure to organize this literature, right? And maybe we can then that intellectual structure can also help us to design new systems. And maybe this would even help us to get towards a theory of these learning and reasoning systems, because currently the literature is very empirical, right? The literature is always of the style that I just said. Like, okay, now we are persons A and B, we built this system, we ran the standard benchmarks, it does better than the previous ones, end of paper, right? That's not a theory, right? That's alchemy. Right? So the alchemists, they did this, right? So they took different substances, they put them together. Sometimes it exploded, sometimes it didn't. But there was no theory. And it took until modern chemistry, until we get the periodic table and the notion of the elements and molecular structure that we can now we can actually predict if you put two stuff together whether they will explode or not. So that would be the long-term goal, but we're not there at all. So what I'm going to give you today is only a sort of an abstract way of thinking about these systems so that you can read a paper and much more quickly understand what it's about. And this is inspired also as a way of building systems. And this is inspired by software engineering. So software engineering did this, right? So this was the software engineering crisis in the 70s. This was, people did this. They wanted to build a system and that was it. There was no theory of how to build these systems. right? And then, so the Gang of Four wrote this famous book on design patterns, right? And now if you want to build a system, there's a book that tells you what design pattern is relevant for the kind of system that you build. And these design patterns, so here they are from the book, they are organized in a family, and you can find your way around in this family of architectures, and then use that to build your system. Okay, so our hope was to come up with something like this. That's what we're going to present now. And how do the software engineers write their architectures? Well, as box and arrow diagrams, right? That's the language in which they express these architectures. And the software engineers were not the only ones to do that. The knowledge engineers did the same, right? So in the 90s, they developed this theory of different types of tasks, knowledge-intensive tasks. So you could do either diagnosis or design or monitoring or all kinds of tasks that you could do with a knowledge-based system. And then for these different tasks, there were different standard architectures, right? So if you were trying to build a diagnostic system, you knew what kind of architecture to start with. And how did they write down their architecture? Again, as diagrams of boxes and arrows. Okay, so we've been also trying to do this. There's 2 papers which underlie the work. So these are the archive versions, but they're both published in different journals. So in the rest of the talk, I'm going to take you through a bunch of examples of these neurosymbolic hybrid systems from the literature, and show you how you would get a high-level architectural view of them so that you can compare them and analyze them, including some papers that were presented here at the conference. And I will always illustrate them with examples from healthcare, actually. So Scott, I'm still very grateful for the name change, because otherwise my examples would not have been relevant for the conference. Right? And of course, the biomedical domain is very suitable for these hybrid approaches, because you have both a lot of data and a lot of knowledge. Right? That's different, for example, from medical imaging, right? So or in general, visual systems, right? These visual systems, they are very low on knowledge and very high on data. Other fields are very high on knowledge, very low on data. In the medical domain, you actually have lots of both, right? So this is really a golden opportunity, the biomedical domain, for these hybrid systems. And there are lots of tasks that you could support with that involve both knowledge and data. And so, for example, selection of patients for medical trials based on their health records. So Jan and I were talking about this yesterday, or of course, prognostic models, or labeling medical images, or extracting relations from text. And we had an example of that today. So there's all these tasks which combine knowledge and data. So we're going to now show a number of these design patterns for hybrid learning and reasoning systems, all with examples from medical AI. Okay. And we're going to use this graphical notation, right? So what is our graphical notation? Has a number of boxes and arrows and 3 main components. So this component does learning, right? So the learning here is you take data and you train a model. Okay, and that model could be all kinds of different shapes, but that's always what learning does, right? You create a model that is somehow an abstraction or a compression, if you want, of the data. That's learning. Okay, and what is inference? Well, inference is that you take a model, could be a logical model or a statistical model, and you take a new piece of data, you combine the model with your new piece of data, and you derive a conclusion. Okay, now that's true for when you've learned some high-dimensional vector space for image classification, and then that's your model. Then you take an unseen image, you combine it with your model, and you get your label out, right? A symbol. But also logical inference, of course, has this structure, right? Except that your model is now not a statistical model, but a semantic model, right? It's a logical theory, and you take a new symbol, or a set of symbols, a query, you combine it with your logical model and deduce a new symbol. And this is called a boxology. And this is a word I didn't know until somebody pointed it out to me. Boxology, actually, it's even in Wikipedia. A boxology is any theory that is expressed in terms of boxes and arrows. Okay, the word exists. We didn't even have to make it up. And so this is a boxology, right? So what we're going to present to you is a boxology of learning and reasoning systems, a boxology of neurosymbolic systems. Okay, so roughly speaking, the squares are stuff that goes in, like data or symbols. Then the models are by these hexagonals, and the processes are by these ovals. Okay, and they come in lots of different flavors. So this is a very coarse, a very rough classification of the different objects involved: data, symbols, models, and processes. And now remember the two bits that I showed you, the bit about learning and inference, right? And you can compose these diagrams. So you've already seen this diagram, that was learning. You've already seen that diagram, that's inference. And then you combine the two, and then you get this, which is your average machine learning system. And your typical machine learning system takes data, it trains to produce a model, then it takes new unseen data and produces inference, uses inference to produce new output. Right, so lots of images, trained, model, new image, inference, label. Right? And that's just by composing these two. So that's the kind of game we're going to play with these images. And these are our atomic components. Right, so inference and the training. Right. And we have also a sort of a linear shorthand for this, right? So this is two pieces of data go in, and then there is a machine learning system that produces a symbol, for example, a label. But this is just a linear shorthand for what's going on in the diagram. So, okay, time for the first real example. You'll see this slide a lot. So, every time there's a new example, you'll see this slide. So if you've been drifting off a little bit, then if you see this slide, then you can step back in, right? Because we're going to a new example. And this is informed learning with prior knowledge, right? So here we don't learn on raw data, but we first do some semantic pre-processing on the data, some semantic inference on the data to produce better data so that our learning works. Right. Okay. So what would be an example of this? And all these examples are taken from the literature, right? I didn't make them up, but they all systems which are published. So your data could be electronic health records. Then your prior knowledge could be ontologies, right? Then you produce enriched health records, where, for example, what you did this morning. You do concept recognition in text over these texts in the EHRs. You annotate them with concepts from SNOMED, so you get enriched EHRs, and then you do machine learning on the enriched EHRs instead of on the raw EHRs, right? And then you have a richer model, and then you can feed in an EHR, and you can do a better prediction, right? For example, a particular disease. And this example of the prediction of colorectal cancer, that's not by accident, because actually that is what Annette did in one of the experiments. She took about 250,000 GP records, and colorectal cancer is one of these silent killers. Right? So by the time you get symptoms, it's already too late. Often it's an advanced stage of cancer. So can you do early prediction? And the hope was, well, can we just inspect the GP records? And is there something in the, at first, kind of innocent symptoms that people may have that would predict possible colorectal cancer? Answer, no, right? 250,000 records. And we knew, of course, which of those patients were ultimately ending up with colorectal cancer. Answer, no signal, okay? But then what they did is they took the patient records, enriched them with concepts from SNOMED in this case, so they could put some stuff together. So some patients were taking a particular drug, other patients were taking another drug, yeah, and so on. But all these drugs were of the same type, right? So if you then aggregate all these individual drugs into the same type, you have a much stronger signal. And suddenly, they could find out that patients who take this drug because they have a stomach, certain type of stomach and gut problems, and they take these drugs, that's an alarm bell for colorectal cancer, right? But on each of the individual drugs that didn't work, and you needed drug bank vocabulary to aggregate all these drugs into a richer pattern, into a richer group. So this is first reasoning, then learning, right? And the paper is here, already quite a few years ago in Computers in Biology and Medicine. Right, next example. So this was first reasoning, then learning. Right, let's turn the tables around and do first learning and then reasoning. Right, and this is your paper from yesterday, Arif. Right, so what Arif did was he first had a learning system, right? A learning system that learned to predict the repurposing of drugs, right? So he started with drug bank. I hope I got this right, otherwise correct me. He started with drug bank. Now he trained this into some high dimensional vector space, some tensor space. Then he took a drug, right, amantadine, and then he used similarity, the geometric properties of the vector space to predict that amantadine might well treat Alzheimer, even though it wasn't never approved for that, right? Still doing all right? Okay, and then, as a regulatory agent, you want to know why, right? Well, here's your 1024 dimensional vector space, that's why, right? So that's not going to work. So what the key idea of that paper is that we're actually going to then use the knowledge graph to make up a potential explanation, right? And then here's the resulting explanatory graph, right? The interesting thing is that this is not how that repurposing was actually found. That repurposing was found through the geometric similarities of that vector space. But this is a reasonable explanation of why that is plausible. So in the explainable AI community, I think they often confuse an explanation of how a model found something with why that is a reasonable result, right? And those are two very different things. My standard example is if I want to know what you had for breakfast this morning, right? I'm not interested in the neural activity in your mind at the time, right? This is how you made the decision, but I'm interested in a plausible explanation of why you made that choice. And maybe you come up with a story about health and preference and lack of time or whatever, right? So this is an explanation that is made up after the fact by reasoning. So this is first learning and then reasoning. Notice that this is the linear notation for first learning, then reasoning. And the previous example was exactly the opposite, right? Then we did first reasoning and then learning. Okay. Let's do another example. And we'll keep doing this until we run out of time. So this is, again, a project from Annette with the people in Munich. So rule fit is a standard rule learning mechanism. It's in the literature, right? And it produces, it's an ensemble method. Okay, so this is, it takes data and it trains and then it produces a model. In this case, it's not a neural model, not some vector space, but it's the model is a set of rules that it has learned, right? That's why I think neurosymbolic is a little bit over-focused because there's nothing neural about this, but it's still a hybrid learning and reasoning system. Okay, so you take patient data, then you train, and you get an ensemble of decision trees. Okay, that's standard stuff. Now, what did they do with the expert rule fit, which is the variety that they designed in Munich? In expert rule fit, you try to inject domain knowledge from experts. So you first go through knowledge acquisition cycle, you get domain expert rules, and you try to combine these with the machine learned rules. So the diagram will now look not like this, right? So we take patient data, then we inject the expert rules, right? And we create a richer ensemble of decision trees, namely an ensemble of decision trees that combines both the rules that were learned and the rules that were acquired from the experts. And you can have all kinds of smart heuristics about how to give preference to the human rules over the machine rules or not, and what to do if they conflict and all that. That's where the secret sauce is, of course, where the magic is. But no, this is only a very small change to the standard pattern, right? And this was the prior rules. So these rules, they then actually even go through a regularization phase where you decide which rules are more important than others. And again, in this generalization of in this regularization phase, you again use human knowledge. Right? So this is getting this is like learning followed by learning, and in both cases you inject human knowledge. Here's the underlying paper for that. This is just because we share the slides afterwards, and then you can look it up if you want. Now, remember this picture that I showed you just for rule fit, right? This is the picture you saw one slide ago, okay? You may not have noticed it, but this is also precisely what you did this morning when you injected an ontology into a learning model, right? So you didn't go to experts and acquired rules and injected the rules. No, other people went to experts, they had an ontology, and you injected the ontology, right? So these are two completely different papers from the literature. Namely, you use an ontology to drive concept labeling in text, it was, right? And in Munich, they use expert rules to learn diagnostic ensemble rule trees. But the architecture is exactly the same. Namely, it's a learning system where they inject a little semantic component into the model. Okay. So talking about learning in a non-neural way, of course, inductive logic programming is a very well-known example that already dates back. Xu did his master thesis on inductive logic programming, and dates back to the 90s, I think, or maybe even older. But even also systems like probabilistic soft logic and Markov logic networks and so on, they are essentially the learning pattern, except that they don't take data as input, but they take symbols as input. So they learn symbols from symbols instead of learning symbols from data. So just as an example, right? So you would give an inductive logic programming system a whole bunch of facts, right? It's like parent relationships and father relationships and mother relationships, and based on a whole bunch of facts, an ILP system, an inductive logic programming system would be able to derive that a parent means either being a mother or being a father. You could derive those rules from those facts. And then you give it a new fact, and from this new fact, it could derive another new fact, namely using the learned rules. Okay, that's what inductive logic programming does. This is now being used a lot for learning over knowledge graphs. Here's another example where this was used. This is for in the rare diseases domain, is a learn new clinical relationships between symptoms and diseases. So this is work by colleagues in Nijmegen, I think, right? So what they do, this is the standard, again, the standard learning pattern, but they inject the SNOMED ontology as part of the training, right? And so they get enriched patient, they can train on these enriched patient records, right? They can learn novel clinical relationships in the form of rules. I have no idea what this rule means, but then if you've undergone some particular procedure at some particular place with some particular outcome, then some particular diagnostic category is plausible. Right? So this is a rule that they learn from these symbols. Right. Right. I think maybe two more examples or so. So this is a pattern that we call from symbols to data and back again. Right, so this is about knowledge graph embeddings. So for those of you who were at the embedding tutorial on Monday, you will know this. So what do you do with graph embeddings? Well, you somehow map the knowledge graph to a high-dimensional vector space, and you want to preserve certain properties. In fact, you want to preserve the relationships. So suppose, now, and what do you want? So you want that if you have a drug 1, and it is related to protein 1 by some relationship, namely drug 1 binds protein 1, okay? Then the drug is a vector, the protein is a vector, and the relationship, the middle part of the triple, is also a vector, namely a vector from the end of the first vector to the end of the second vector, right? Now, if you find another drug and another protein pair, namely drug 1 and drug 2 and protein 2, right? And if that distance between drug 2 and protein 2 is the same as between drug 1 and protein 1, then they are likely to have the same relationship. So that's the reason for predicting that maybe drug 2 also binds protein 2, right? This is the intuitive idea of graph embeddings and link prediction. So what you're doing here is you're starting with a symbolic space, a knowledge graph. You move to a vector representation, so a geometric space, right? Then you use geometric properties here, like similarity in the geometric space. And then you use those geometric structural properties and translate them back to the knowledge graph. Namely, you add a link to the knowledge graph that didn't exist, but that's plausible given the geometry of the space. Okay, so that's why we call this from symbols to data and back again. And here's an example of that. So, okay, I already gave the example. This is unwanted side effects in polypharmacy, right? So one drug is fine, 2 drugs is fine. Most people of my age take 4 drugs, okay? And nobody knows what are the total interactions of all of these drugs. So there's a lot of work on trying to predict these polypharmacy side effects. And you do this by embedding, then you give it a new drug, and then you hope that you can, by geometric similarity, you can find potential adverse effects. Okay. This is work published in EMEA. Okay. Learning multiple representations. I'm going to skip this for reasons of time. You get the picture by now, right? I want to just give you one last example, and that is how you can do the same task in multiple ways, right? So, okay, now we have a whole bunch of these systems, and at least we now have a vocabulary to talk about these systems at a higher level of abstraction, right? We have these loosely coupled components, and we can put them together, and we have a high-level architectural story. So I hope that you two guys recognize your system in these pictures. Otherwise, we failed. But you have these tasks, and how do we bind tasks to these architectures, right? So I have a prediction task, or a classification task, or a labeling task. Can we develop a theory that links these tasks to these architectures? And here's the beginning of some thinking about that. So this is about the living guidelines. Okay, so we all know medical guidelines, right? They're important. They drive a lot of the diagnostic and therapeutic procedures in medicine. And they, if you're lucky, in a rich, well-organized country like the Netherlands, they get updated every 5 years. Okay, and mostly that we don't make, right? So that means that the best available care is always at least is often 5 years out of date. And I think that most of the time we don't even make that 5-year cycle. So can we not make these guidelines more living? Can we that they get updated as soon as there is sufficient body of evidence in the literature? Now people write meta reviews and so on. Can we not update those, or can we update them based on a body of patient records? Because often there is a national guideline. Now you shall use a certain MRI scan for this, and then you're in a hospital. Yeah, well, we don't have that machine. So then the doctors do something different. So in that hospital, there should be a locally updated version of that guideline, and that happens. Currently, it happens by hand, right? So can we not automatically spot those deviations and propose modifications to the national guideline for local circumstances? Okay. So this requires that you have a computer interpretable version of this guideline. And there is a rich body of literature. I think it came up yesterday. Languages like ASBRU and Proforma, and there's a whole library of computer languages to represent these guidelines in computer interpretable format. So here's one option. Okay, so you take an EHR, you learn rules from those EHRs, right? So what do doctors typically do? assuming that doctors most of the time do the right thing, right, or the best possible thing. So this is what an abstraction of what doctors really do, learned in rules, right? Then you take the original guideline, right, and you take a new patient, but you don't treat it only under the original guideline, but you treat it under a combination of the original guideline and what doctors do in practice, which you could see as the updated version of the guideline, right? Often doctors do something different from the guideline because they already know that some new treatments or some new drugs are not mentioned in the guideline, right? And if you then would only use the original guideline, you would never benefit from the fact that your colleagues are already prescribing new medicines. So this is one way of doing it, right? This would make your guideline more up-to-date, updated with the recent behavior of your colleagues. Here's another way of doing it, namely that you take EHRs, you learn those rules, right? And then you try to learn a single new model, which is the combination of the original guideline and the rules that you just learned. So rather than using separately two models to make decisions, now you try to integrate them into a single model and then use that model for us to diagnose or treat patients. And the third way of doing this is that you take EHRs, you take the original guideline, and you try to update these guidelines with these EHRs, right? So this is the picture that we've already seen. This is a standard machine learning step, but you inject the semantic model into the step, and you injected the concept hierarchy, the people in Munich injected rules, and here you inject the computer interpretable version of your guideline. Okay, but it's the same pattern. So now we have done the same thing 3 times. We've tried to construct more living guidelines by 3 different neurosymbolic architectures. Okay, right. So time to wrap up. So our goals were twofold, right? Our goals was, okay, well, help us to read the literature, right? Give us a higher level view of what these papers do, so that I can compare and contrast and classify them. And the second goal was create somehow a beginning of a theory about these architectures, so that we can start thinking about them at the architectural level, rather than only at the very detailed algorithmic or mathematical level. And it's very hard to compare these systems. So those were the 2 goals. And I think that I would claim that we have a set of these reusable architectural patterns. We have by now debugged this against 70 different papers in the literature. And actually, colleagues in Vienna, how many papers did they read, Annette? 150? So they took, yeah, your face, my feeling, right? So this is people in Vienna. So they took semantic web systems, and semantic web systems often combine these learning and reasoning. So they read the entire semantic web literature, hunting for systems that combine learning and reasoning, read 150 of them and captured them all in these kind of patterns and classified them, right? And we showed, yes, this is also relevant for biomedical applications. So where do we want to go next? Well, yesterday we heard that together with the people from Vienna, we have a ACM computing surveys paper accepted. So they don't need an applause because they get a paper in a big name journal. So that's great. Yeah. So this is really beginning to become a stable set of patterns now. And we want to continue this exercise of mapping tasks to architectures, right? And I think you can't do this in general. You need to do this in a domain, and the biomedical domain would be excellent. And maybe it's still too broad. And so what architectures would work for which kind of tasks? Because that's ultimately what the software engineering people did with the Gang of 4. Then, of course, all I've shown you is pictures, arrows and boxes, right? Boxologies. So you would like them to be more precise. So we're working on a grammar to describe these pictures, hence the linear form. A colleague in Germany who we didn't know, but he picked up our paper and formalized the composition of these diagrams in category theory. So you take diagrams, compose them or decompose them, and you use category theory to describe that process. And we would like to describe these diagrams in Hoare style pre and post conditions, right? So that you could compose them and then do proofs about the resulting diagrams. And Annette is also working on a project where, well, why are there only two components, namely machines that learn and machines that reason? Why are there not three components, machines that learn, machines that reason, and humans? Right. So this is this sort of human-centered AI where systems are not closed, autonomous, but they're open with humans in the process. And can we come up with a similar theory for that? Okay, so thank you. Of course, this is collaboration with Annette, but I've mentioned that people from TNO in the Netherlands that we work with, people in Spain that help us with reading the medical literature, and the people in Vienna that I've mentioned. Thanks very much.
I'm trying to see if I understood and maybe point to inject to humanity. It's where you would like to have new sets of guidelines.
Yes.
Maybe you can help me find that slide. I don't know, but
yeah.
And the question is, in practice, you might have a clinic or a practice that is, let's say, maybe not ethical.
Yeah.
But is actually consistently so.
Yeah. Yeah.
So would the outcome be?
Yeah.
Guidelines.
Yeah, definitely. Yeah.
So perhaps a point to inject a humanity
right.
check at that point.
Absolutely. Yeah. So I think the more general point you're making is, well, the question is you're training rules that capture the current behavior, and you're injecting that current behavior into the national guideline. Does it get better or worse? Well, it depends on what your doctors have been doing, right? And if they have been making mistakes or unethical behavior or discriminatory behavior, which happens now across patient groups. So yeah, that's certainly true. And I don't think anybody would ever do this in a closed loop system, right? You would want to inspect what that is. So that's certainly, that point is certainly well taken. Absolutely.
So I've never actually seen a talk on this stuff at this level of abstraction. And we all like a good abstraction. So that's really good and really exciting. One of the things you talked about the beginning about the design patterns and the whole sort of boxology that's there, and that's been really transformational in many areas of software engineering. Sometimes you're looking at some Java libraries, you think maybe it's gone a bit too far. They stick design patterns on top of design patterns on top of design patterns. But one of the nice things about that particular representation, that boxology is a sort of UML representation, is a fairly standard methodology from how you get to there to how you turn it into something that you can make it non-abstract. You can click on it and make it run. So I'm not going to ask the question because you've obviously already got to the question.
No. So you're saying, okay, so okay, diagram is nice. Now how do I get the code?
Yeah.
Right.
Or the architecture or whatever.
Yes. Yeah. So until recently, I had it on our to-do slide. It also said link this with software libraries. Right, and there are both in the machine learning and in the machine reasoning world. There are lots of software libraries to do stuff, right? For ontological inference, or for consistency checking, or inductive logic programming, or TensorFlow or whatever. And so, ideally, you would like to tie parts of these boxes to code or libraries of code so that you could compose them. We took it off because we thought this was so far away from what we knew how to do that we didn't dare to say it out loud anymore. But now that you're forcing me to, absolutely, yeah, that would certainly be the dream. Yeah. Want to collaborate? Right. Right. Yeah. Okay. Michel.
Hi. I've had a sort of a long-running dream of having long-running clinical trials where you basically you've got a clinical trial, it has case report forms and all this negotiation with the drug administration, or like FDA or EMA or whatever. And at the end of that, you kind of throw all that stuff away. You say, okay, we've got our evidence, and we're going to recommend that we're going to approve the drug, and it'll go into some clinical guidelines. Whereas if you have sufficient coding, like if you look at the details of that clinical trial, there were certain admission criteria, there were a bunch of concomitant medications and stuff like that. And if you basically liberalize that so that there's more concomitant medications, you can run that across the whole population of people. You don't have to stop that clinical trial when it starts being used. And so I think that fits into one of your one of your models
Okay.
of the
Okay.
the system. Yeah, I see where I'm going.
Okay. Okay, so now that sounds like a task we didn't really think about a lot, but so we thought a bit about using machine learning to extract candidates for trials. But yeah, that would be interesting, maybe. Sure, Michelle.
Yeah. Oh, thank you so much. This was a very nice talk and certainly helpful indeed as we get inundated with different system descriptions and so on. I think it helps us to think about it. But perhaps the question that still remains in my mind is, will any of this work? So if the goal of neurosymbolic AI is to improve the overall quality of the, say, predictions or answering questions, are any of these architectural combinations going to lead to what we're looking for?
Okay, so that's not a question about our notation, but it's a question about the neurosymbolic enterprise in general, right? And I think definitely yes. So now remember my joke at the beginning where I said, if a machine learning person says, I can't solve your problem because you don't have enough data, it's because they don't have the right algorithm, right? Often injecting this knowledge makes these machine learning algorithms much more data efficient because you're telling it stuff up front. You're giving it much more bias, and therefore it can learn from a lot less data. So that will be one improvement. Another one is also one that we're working on in the lab is you can enforce safety constraints. So reinforcement learning, there are parts of the behavioral space that where you don't want it to go, right? Because they're unsafe. And you can impose these constraints up in front. So that's imposing symbolic constraints on the behavior of a neural agent that you're training. So that would make it more efficient or more safe. It would make it more explainable. So I honestly think, and I'm not in selling mode here, but I honestly think that some of the big drawbacks of machine learning, namely, it's not guaranteed safe, it doesn't generalize well, it's too data intensive, it's black box, that many of these big problems become solvable or a bit solvable, and they become less by injecting symbolic knowledge. Yeah.
Thank you.